Hey everyone, and welcome. Today we're tackling Leetcode problem 717, 1-bit and 2-bit characters. This is a great problem to practice array traversal and careful reading. We'll break it down into simple steps and look at a couple of cool ways to solve it. Let's get started. Alright, let's understand the rules of this world. It's pretty simple. There are only two kinds of characters. The first type is a 1-bit character, and it's always just a 0. The second type is a 2-bit character, and it always starts with a 1, followed by either a 0 or another 1. That's it. So what's our job? We get an array of these bits, and we're guaranteed that the very last bit in the array is a 0. Our task is to decode the entire sequence and determine one thing. Is that final character forced to be a 1-bit character, the simple 0, or is it part of a 2-bit character? Here's the problem statement from Leetcode. The key is that the decoding must be done from the beginning of the array. You can't just look at the end. You have to see how the bits group together from the start to know what the final character is. Let's walk through an example. Imagine we have the array with 1, 0, 0. We always start from the left. The first bit is a 1. According to our rules, any character starting with a 1 must be a 2-bit character. So we group the first two bits together, the 1 and the 0. That's our first character. Now we move on. The next bit we look at is the final 0. A 0 by itself is always a 1-bit character, and since that was the last character we decoded, the answer is true. The last character was a 1-bit character. Okay, let's try another one. 1, 1, 1, 0. Again. Starting from the left. The first bit is a 1. So we know it's a 2-bit character. We consume the 1 and the next one. Our first character is 11. Now, we're left with 1, 0. The next character starts with a 1, so it must also be a 2-bit character. We consume the final 1 and 0. The last character we decoded was 10, which is a 2-bit character. Therefore, the answer is false. Just a quick heads up. We'll be walking through the solution using Python, but if you use another language, don't worry. The logic is the same, and I'll show the full code for Java, C++, and JavaScript at the end of the video. Alright, our first approach is pretty intuitive. We'll just do what we did in the walkthroughs. We'll start a pointer at the beginning of the array. Then we'll walk through it, deciding how many steps to take. If our pointer is on a 1, we know it's a 2-bit character, so we jump ahead 2 spots. If it's on a 0, we know it's a 1-bit character, so we just jump ahead 1 spot. We'll keep doing this until we can't jump anymore. Okay, we've got the idea. Let's see how this simulation translates into code. I'll show the full Python function first, and then we'll break down the key parts to make sure it's crystal clear. Here's the code for our pointer incrementing approach. It's a simple loop that moves an index I through the array until it reaches the end. Let's look closer at how it works. First, we initialize our pointer, which we'll call I, to 0. The core of this solution is the while loop. Notice the condition. We keep looping as long as I is less than the length of the bits list minus 1. We do this because we're always trying to figure out the start of a character. Once our pointer is at the last element, we can't possibly start a new character, so we stop. Inside the loop, we have a simple check. We look at the bit at our current position I. If that bit is a 0, we know it represents a 1-bit character, so we increment our pointer I by 1 to move to the next character's starting position. If the bit is a 1, we know it must be a 2-bit character, so we need to skip over both bits of that character. We do this by adding 2 to our pointer I. So after the loop finishes, what does our pointer I tell us? Well, if our sequence of jumps landed exactly on the last index of the array, it means that the final character must have started at that position. And, since we know the last element is always a 0, this means the last character must be a 1-bit character. If our pointer overshot the end, it means the final 0 was consumed as part of a 2-bit character. So we just return whether I equals the last index. Simple as that. Now for a second, much more clever approach. This one realizes that the entire beginning of the string doesn't really matter. All that matters is the block of 1s right before the final 0. Think about it. A 1 pair decodes to a single character. So if you have an even number of 1s before the final 0, they all pair up with each other. This leaves the final 0 all by itself, as a 1-bit character. But, if you have an odd number of 1s, the last one will be left over, and will be forced to pair with the final 0, creating a 2-bit character. This is a really neat trick that avoids iterating through the whole array. Let's see what the code for this greedy approach looks like. It's surprisingly short. Here's the Python code for the second approach. As you can see, it works backward from the end of the array to count those trailing ones. Let's break it down. First, we set our pointer I to the second to last index in the array. We don't need to look at the very last element, because we already know it's a 0. Our goal is to find where the sequence of ones just before it begins. This is the core of the method. We have a loop that moves backward. As long as two things are true, we're still inside the array, and the bit we're looking at is a 1. The moment we find a 0 or fall off the beginning of the array, the loop stops. At the end of this loop, I will be pointing to the position of the last 0 before our block of trailing ones. Finally, the return statement. The expression here calculates the number of ones we just counted. Then, it uses the modulo 2 operator to check if that count is even. If the number of trailing ones is even, the expression is true. If it's odd, the expression is false. This perfectly matches the logic we talked about before. So how do these two solutions compare? Well, in terms of performance, they're actually very similar. For time complexity, both are big O of n, where n is the number of bits in the array. In the worst case, both methods might have to look at every single element. And for space complexity, they are both big O of 1, or constant space, because we only use a single pointer variable and don't create any new arrays. Alright, that covers the logic in Python. As promised, for those of you who code in other languages, I'm about to show the full solutions for Java, C++, and JavaScript. I won't be breaking these down, so just pause the video on your language of choice to check it out. Alright, as promised, here is the full solution in Java. I've implemented the first approach here, the pointer incrementing method. You can pause the video here to take a closer look. Next up, here is the C++ version of the solution. Again, it's the same iterative logic. Feel free to pause and review the code. And finally, here is the solution in JavaScript. Hopefully, seeing it in a few different languages helps solidify the concepts we've discussed. So let's wrap it up. We saw two great ways to solve this problem. The first approach was a straightforward simulation, just walking through the array and making jumps. It's reliable and easy to think of. The second approach was a bit more clever, realizing that we only need to look at the pattern of ones at the very end. Both solutions are highly efficient, which is awesome. Alright, before we end, I want to quickly show you a personal project I built to solve a problem that always drove me crazy. It's an app called My Daily To-Do. My biggest frustration with every other to-do app was retyping the same things every single day. Go to the gym, review code, work on the daily Leetcode problem. You know the drill. So I built my app around one simple but powerful idea: separating your routine tasks from your one-off tasks. Routine tasks, marked with the little refresh icon, automatically reset for the next day. One-off tasks, like ship new feature, get the little puff of smoke icon, and they disappear for good once you're done. This small change turns a dumb checklist into a smart scheduler. If that sounds useful, you can try it right now on the web. The link is in the description. And one more thing I want to make super clear. Right now, as a thank you for being an early supporter, the app is 100% free. There are no ads and no subscriptions whatsoever. This means you get access to everything, including really powerful features like presets, which let you save entire task lists and load them with a single tap. Now, down the road, creating new presets will likely become part of a premium plan to help support the channel. But, and this is the important part, any presets you create now, while it's all free, are yours to keep and use forever. So it's the perfect time to check it out on the web, play with all the features, and build out your perfect setup at no cost. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems. So if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. If you want to support the channel, a few people have asked how I plan my solutions. I'm a big fan of sketching out the logic and data structures on a tablet before I code. It really helps. I've put affiliate links in the description to the tablet I use and a few other good options. Using those links doesn't cost you anything extra but really helps me out. Or, if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.